when we have the probability of multiple events, sometimes it's just like what we've been talking about, which is when you're trying to find probability and it has to do with things that all have to happen at once. You know, we talked about if you want 2 7s and you have to have another 3 cards in your hand. But the and piece means we have to multiply those things together. So that's not going to change as we look through this section, but we do have situations where we want to talk about either this happens or this happens, and that's a little bit different. So today we're going to find the probability of events A and B. Not a big deal. We know when you want 2 things to happen once you multiply, but we're also going to talk about what if it's one or the other. So big difference. Doesn't seem like it. 3-letter word, 2-letter word, and or, but it's a huge difference in probability. So this one right here, I want you to look at player 1 and player 2's tallies over there. And it's going to ask us which one is which when we read through this. It says you and your friend take turns rolling 2 standard number cubes. If you roll a sum that's either odd or a prime number, and you have to know what the prime numbers are in order to do this. They are the numbers that can only be divided by 1 in themselves, starting with 2. 2 is considered to be the first prime number, so 2, 3, 5, 7, etc. So you roll 2 dice, and if you get something that's odd or a prime number, you get a tally. You won. If your friend rolls a sum, it has to be both odd and a prime number in order for them to get a tally. So, which of these 2 scores is probably yours? And it's easier for you to score a point than it is for your partner to score a point because they have to have both conditions met. You're saying either this happens or that happens, and I get to count it. But hers, they both have to happen at the same time. So you're definitely player 1. You should be ahead unless things are going really weird as you go through this. And we talked about that too. Toss a coin in the air 10 million times. You're not guaranteed that 5 million times you're going to get heads. I mean, that's the theoretical probability, but it's not reality. So we're not going to worry about how many turns you've taken and all that, because that's just a matter of counting. But it's important to know which person has the advantage. Because if you want a fair game, you'd hopefully get the advantage. That never happens in gambling, by the way. In gambling, the house always has the advantage. That's the reason it's called gambling. They have the advantage over you. So, essential understanding. To find the probability of 2 events occurring together, you have to decide whether or not one event occurring affects the other event. So, it could be that when you are doing your experiment or playing cards or whatever it is, the circumstances change between the time that you do the first thing and the second thing. Let me give you a for instance. Let's just say there is a deck of cards up here on the cart. And I want to know the probability that I will get a 4. So I go ahead and pick a card, and it's not a 4. And I set it down over here. Now somebody says, well, pick another one. Let's see if you get a 4 this time. Well, now I don't even have 52 cards left over here. Now I only have 51 because I took one of those cards and I set it down over here. So the circumstances have changed. The total has changed when I talk about my counting principles. So when the occurrence of one event does affect how a second event can occur, those are called dependent events. It changed the circumstances. I took a card out, I did not put it back in. Now I don't have 52 cards anymore. That changes the probability when I go to pick another card. Absolutely does. However, if I said, I pick a card out, it's not a 4, I put it back in, I shuffle them all up again, and now I'm going to try and get a 4 again. The probabilities are the same because I put the card back. And that means they are independent events. One doesn't have anything to do with the second one. They are totally separated. So it just kind of a reset button, you know, as you go through there. So what they want us to do is just look at some of these and decide, do these two have anything to do with each other? are they going to change the probability of one versus the other? So this one says we're going to roll a number cube. And it's not rolling this morning. Okay, we're not going to roll a number cube. And then we're going to spin a spinner. Great, Smartboard's mad that I'm recording. It's not going to let me do any of that. If we roll a 5 on this die, does that guarantee we're going to get orange over there? Kind of silly, right? There's no way those two things have anything to do with each other. These are independent. Oh yes, it's very mad at me. Usually I can write over the top of the visuals here, but I won't let me. So those are independent, have nothing to do with each other. Pick one flashcard, then another, from a stack of 30 cards. Did we replace the card? So we've just changed the circumstances. That means because we took that one card, the second probability is going to be affected. So this one is dependent. Unless it says we're replacing it. That replacement, that's the reset button. That's what we're hoping for, that we just start all over again. Alrighty, got it. 1 says, you select a coin at random from your pocket. You replace the coin and you select again. Are your selections independent events? Yes or no? Yep. You know, you put it right back and you just hit the reset button and you went again. So what's really happened here is that the circumstances have been reset back to the original. You put it back and you start it over. You know? When you do that, it's like a reset button. You're back to the original circumstances once again. So that's what makes that independent. Like I mentioned, our objective today is to talk about what happens when you want this and this to happen. Well, you can see right here, we're just going to multiply. Well, that's if A and B are independent events. So what we do is we think, okay, if I do this first thing, does that have anything to do with the second event? If I'm going to roll a die, does that have anything to do with spinning a spinner? No, absolutely not. So I just find the probability of rolling a 5 on the die, and then find the probability of spinning orange on the spinner, and I just multiply those two things together. That's what AND does. If you want it all to happen at one time, that's AND. So this says we're going to find the probability of independent events, and I really wish they wouldn't have told us they were independent, so that we can see. It says at a picnic, there are 10 diet drinks and 5 regular drinks. There are also 8 bags of fat-free chips and 12 bags of regular chips. If you grab a drink and a bag of chips without looking, what's the probability that you would get a diet drink and fat-free chips? All right, so there's 2 things going on here. You're going to pick a drink, and you're going to pick some chips. Does it say up there that if you take a diet drink, they're going to force you to pick fat-free chips? Nope. You get to pick what you want. They're independent. So what I need to do is figure out the probability that I'll get a diet drink. How many diet drinks are there? 10. Out of how many total? 15. Chips. How many bags of chips are there altogether? And how many of those 20 are fat-free? Now if we're going to do this by hand, we'll probably reduce these two. So we divide the 10 and the 15 by 5, and we would divide the 8 and the 20 by by 2. And that's not by 2, we go by 4. Bigger. Go bigger, Cedar, huh? There we go. Go bigger, go home. All right, so then we just multiply top times top, bottom times bottom. And with this one again, we could just leave it 4/15, We could write it as a decimal. We could write it as a percentage. All of those are valid ways to answer this question. So it's totally up to you at that point. Which means you could have just punched into your calculator 10/15 times 8/20 and gotten the answer if you wanted to. Wouldn't have to do the reducing. Alrighty, down here it says in problem 2, what's the probability that you get a regular drink and regular chips? Let me scoot that up so you can still see it. There. So we are still looking at picking a drink and picking some chips. But this time we want a regular drink. So what's the probability you'll get a regular drink? 5 out of 15. What's the probability you're going to get some regular chips? 12 out of 20. So let me write it down over here. I'm just doing some of the, I shouldn't skip steps like that. I got it. So when you look at your notes, it makes sense. We've got 5/15, 12/20. And one of the things we can do with fractions is we can cross reduce. So these 2 3s would cancel out. And you get 1/5, or if you wanted to write it as 0.20 or 20%, you can do that. So however you want to go about it. So that's and. Now, 2 events that cannot happen at the same time get a special name. They're called mutually exclusive events. And we looked at one right off the bat where we said we're going to roll a die and we're going to spin a spinner. They have nothing to do with each other. Absolutely nothing to do with each other. They're mutually exclusive events. If A and B are mutually exclusive events, then the probability of A and B is 0. So mutually exclusive, they cannot happen at the same time, is what they're saying. Can't do the 2 things at once. So problem 3 is, do we just recognize mutually exclusive events when we see them? You roll a standard number cube, a die. Are the events that we see here mutually exclusive, and explain? Can you, with one roll of the die, roll both a 2 and a 3? Not on a standard number cube. It's going to land flat on one side. So these are mutually exclusive. And that's because one or the other has to happen. You can't roll both a 2 and a 3. Can't happen. Never seen a number cube land on like the edge. Doesn't happen. They're built that way. So B says, how about rolling an even number and a multiple of 3? Even numbers on the die. Any of those multiple of 3? Yeah, we got trouble. It's the 6. So these are not mutually exclusive. Because 6 is both even and a multiple of 3. So they're not mutually exclusive, because they could both happen at once. If somebody rolls a 6, it could happen. Got it. 3A says rolling an even number and rolling a prime number. Remember the primes. Got 5. Can we roll an even number that's also a prime number? 2. Who's the problem? Not mutually exclusive. Just put the 2 in quotation marks. So meets both criteria. It is an even number and it is a prime. Rolling an even number and rolling a number less than 2. Got any even numbers on a die that are also primes, less than 2? We don't have any primes that are less than 2. So no, there's no way that both of those can happen at one time. Those are mutually exclusive. So far it's just been a lot of vocab. You know, the probability is not really a big deal at this point. It's not anything different than what we were doing in the other sections. So now we have to change things up and say, well, instead of and, what if it's this or this that can happen? So put your stuff down for a second. And anybody that's wearing gray, I want you to stand up. If you have gray on today, please stand up next to your desk. Take a look at all the other people that are wearing gray. Those of you that are sitting down, look at the people that are wearing gray. These are people wearing gray. Please sit down. People that are wearing gray. Now I want people that are wearing tennis shoes to stand up. If you're wearing tennis shoes today, please stand up next to your desk. Okay, take a look around. Please have a seat. So if I wanted to find the probability that people in here are wearing gray or that they're wearing shoes, there's an issue. I'd count all the people that were wearing gray, say that's the number out of the total. Then I'd count all the people that stood up for wearing tennis shoes, take that out of the total. And with or, you're supposed to add those two things together, unless somebody's been double counted. Did we have anybody, raise your hand, who wore gray and had tennis shoes on? Nobody? Jack, right here. Good, you paid attention. Jack was in both groups. So we have double counted Jack if we do that. So what we have to do is say, okay, I'll count up how many were wearing gray. I'll count up how many were wearing tennis shoes. But I have to subtract Jack because he was in there twice. And that's how the formula works. So if we want the probability of A or B, we find the probability of A, we add it to the probability of B, that then we have to think for a second. Is there any chance that anything was double counted? Is there something that was in both of these groups at once? Because if it was, we have to subtract that off. Now, we just got done talking about mutually exclusive events. Mutually exclusive events are where that can't happen because they're two totally separate things. So if they're mutually exclusive events, notice this is gone because there wasn't any overlap. They were mutually exclusive. There's not going to be anything that we can subtract away. There will be nothing in that overlap group. So down here, it says we're going to find the probability for mutually exclusive events, but that's not usually how I go after them. When I see or, I just write the formula down and I think, is there anything in this overlap? So at your high school, a student can take one foreign language each term. About 37% of the students take Spanish. 15% of the students take French. What is the probability that a student chosen at random is taking? Had to read all the way through the problem to get the important part. Spanish or French. So I think to myself, I've got this formula, probability of Spanish or French. What I'm supposed to do is find the probability that they're in Spanish plus the probability that they're in French minus the probability that somebody's been double counted because they're in both Spanish and French. Well, they flat out gave me probabilities, didn't they? What's the probability somebody's taking Spanish? 37%, because we're going to do math with it. We change it back to a decimal. What's the probability that somebody's taken French? 15%. What's the probability that there's a student that's taking both Spanish and French? Find something in there that tells us what the probability that they're taking both Spanish and French is. If you're saying it's 0, what told you it was 0? They're only allowed to take one. They can't take them both. The rules say can't do it. So that's what makes this mutually exclusive. But the problems you're going to get in the homework don't come with that header. Find the probability for mutually exclusive events. So you have to think your way through it. Could a student take both Spanish and French? No, the guidelines say right here, you're only allowed one. That's it. They don't want you studying 2 at a time. So really all we have to do is add those 2 together. And if we wanted to, we could change it back to 52%. Since the problem came in percentages, that is probably the best way to go. So our probability that they're taking Spanish or French is 52%. You got it? So as I mentioned, usually they're not going to come out and tell you they're mutually exclusive. Usually you have to think your way through them. This is a good problem to give you candy partners. So go ahead and start working on this one. And I will get you a candy partner and we'll see how everybody's picking up on this objective of finding probability of A or B. Just like in part A, where I said, is it a big deal they gave us 3? And you're like, no, you just add them together. Of course, that's all we do. Or means it's one or the other. We do stop and think, is there any overlap? But they already told us, one language, that's it. So with percentages, we're going to know the percentage doesn't matter according to how many students they're talking about. It just matters that we know the highest percentage. That will give us the one that has the most students. So now we got a problem. The next problem deals with knowing the colors of stuff, and you have a black and white packet. So everybody's got a bag at a desk somewhere near them where we're probably going to have to do some coloring. Or in the past, I know people have gone through and put like a G on the green ones and an R on the red ones and that kind of thing. Because this time we're going to see some events that are not mutually exclusive. And as we talked about, what we're going to have to do is add the probabilities together, but then we have to subtract anything that's been double counted, anything that's in the overlap. So your little blank up here was the subtract word. If you want to get that filled out, then I'll scroll this up a little bit because I know it's hard for some people in the back to see the colors. So little blank should be subtract. I'll move that up even farther so everybody can get their colors on it. Whether or not you want to use the highlighters and stuff from the bag, or you just want to go ahead and write R for red, whatever you need to do. We obviously have some overlapping groups here. We have some red circles and we have some green circles. They're both circles. So if we talk about the group of circles, there could be some overlap there along with the colors. So this is where it becomes important for us to say, okay, or means add, but if there's anything that's in the overlap that could be counted in both groups, we're going to have to subtract that. Anybody need more time to draw? It is orange, yeah. It's very close to their red there, but it's supposed to be orange. All right, this one says, suppose you reach into this dish, you can't look, deep dish, and you can't see it, and you select a token at random. What is the probability that the token is round or green? So we're going to need the probability round or green. Well, that's going to be the probability that it's round plus the probability that it's green minus the probability that it's round and green. So we have to do that little piece of subtraction there. Round. How many round things we have up there? 5. Out of a total of how many? 9. Probability that it's green. How many green things? Out of how many? 9. Not going to reduce it because we're adding. And when we're adding, we need a common denominator. Did we have any that were both round and green? 2 of them. So when we're talking about or, we don't want to reduce. We want a common denominator. We've got 5 ninths plus 3 ninths, that's 8 ninths. 8 ninths minus 2 ninths is 6 ninths. Now we reduce at the end and say, okay, chances are 2/3. That's what we have there for a probability. Again, you change it to 0.666, repeating forever, or say approximately 67%. But up here, we're just looking for our answer. Now do notice this. Do you see how the reduced answer isn't up here this time? They do that sometimes with multiple choice. It's called a distractor. So you look and you say 2/3. Oh, it's that one. Because you were just looking for a 2. That's called impulsivity in testing. You don't want to be impulsive. You want to realize, wait a minute, that wasn't 2 ninths, it was 2/3. Well, they didn't use 3 up there. I better go back to this answer. And there it is. So you just take your time when you're doing multiple choice and things go just fine. You and your partner, please do 5A and B. Ooh, I'm going to leave the picture here though, so it's a little easier for you to see. There we go. Talk to each other when you're done. I know there's still a few people that are still working on this, but most of you are probably ready. They ended up being the same answer, right? They both were what? 5 ninths? They both were 5 ninths in the end. So the big piece here was really, do we understand that when we're talking about or, we have to take off the double counting? The wearing gray and tennis shoes, Jack Berry. We have to do that. So 2 formulas today. The and, gosh, I don't even see that as a new objective. We kind of already talked about that. But the or was the other one. So 4, 3, 2, 1, 0. And at this point, maybe you're saying, really, we're done? That's it? Probability is really just like that? Yeah, it is. Thank your partner for their wonderful help.
Yeah.
We've talked about how probability is often the butt of jokes, and that's because probability is one of those things that you can do a little manipulation with. So this says, the stupid state wants to raise money by expanding the state lottery. Now people will spend more of their hard-earned money chasing impossible odds. Yeah, that's what's so great about the lottery. Why does that make the lottery great? It's a tax on people who can't do math. Please leave me alone. Now if we could just tax general stupidity. 4 lotto tickets, I am guaranteed to win. There's always somebody that just doesn't understand, the probability piece. So don't be one of those people. Be one of the people that says, oh my goodness, chances I'm going to win this pretty doggone low. So I'll spend what I can afford, but I'm not going to go in and spend my whole paycheck on pull tabs. Not a good plan. There it is. Oh, that worked out today too. Cool. The way you guys were going through this isn't going to take very long at all.